Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to just go through an example of acceleration where there's both a tangential and a centripetal acceleration. So let me explain what we're looking at here. Imagine this circular racetrack here with a 100-meter radius, and this green car starts here at t equals 0, its velocity is 0. But the driver partially steps on the gas, and we're going to imagine a tangential acceleration of 2 meters per second squared for this problem. What we're going to try to do is calculate the acceleration vector of the car 10 seconds later, assuming that that tangential acceleration stays constant. So the first thing I'd recommend here, let's get some sort of idea for where this car is and how fast it's going 10 seconds later. So when studying motion, I always like to use a velocity graph to do that. I'm going to make a slight qualifier here, though. I'm going to make this a graph of the car's speed against time. And the reason is because the velocity is constantly changing in direction. So this is going to be speed against time. If our tangential acceleration is constant, that means that this is going to be a linear graph. It's going to look something like this. And the slope of this line is going to be the rate that the speed of the car is changing. The slope of that line is going to equal 2 meters per second squared. Now, 10 seconds later, that's going to put us here. This distance we can go ahead and just calculate by this. Acceleration, tangential acceleration, is equal to change in speed. I'll put change in v here, but again, that v is speed, no vector symbol, over change in time. In this example, the acceleration is 2 meters per second squared. The change in time is 10 seconds. I'm going to go ahead and just multiply by the 10 seconds. That's going to give me the change in v, and I get 20 meters per second. So on this graph, this vertical height here is going to be 20 meters per second. The distance that the car traveled, we can get from this area right here. That's going to be 1/2 10 seconds times 20 meters per second. That's going to be 100 meters. Right? Now this happens to have a radius of curvature of 100. Those are completely unrelated. That's just kind of coincidence because I chose this 10 seconds and this 2 meters per second squared just completely at random. So this does not have anything to do with this radius. All right, so just to give us an idea of where that car is. So when you're looking at these little sector problems like this, right? Let's see, S equals R times theta. That's not what I wanted to say. Here's what I wanted. This distance right here is 1/4 of a circumference. The circumference of a circle is 2 pi times the radius, or 2 pi times 100 meters. If I were to divide that by 4, 2 times 3.14 times 100 divide, oops, calculator's not on, let's try that again. 2 times 3.14 times 100 divided by 4. I get 157 meters. So this is 157 meters to here. That means if our car has traveled 100 meters, that car is right around, maybe right about here. Exact angle, not really important for the discussion. All right. Now I'm going to go ahead and put a picture of that car right there. That's what I was saving this for. I'm going to move that car over to here. I'm going to rotate it, get it going, get it pointed in the correct direction. There we go. So 10 seconds later, this should be the approximate location of that car. Now, the acceleration vectors. I'm going to draw acceleration vectors on that car, and I'm going to draw those in red. Right, so the 3 meters per second squared is still there. So that car still has a tangential acceleration vector that points this way. Whoops. I'm going to draw the acceleration vectors in red. Three meters per second squared. However, in addition to that, this car is undergoing circular motion. So there is also a centripetal acceleration vector pointing towards the center of curvature. So the centripetal acceleration vector of the car points something like this. The net acceleration is the vector sum of the two. So I'm going to go ahead and calculate this guy. Centripetal acceleration is equal to v squared over r. In this problem, the v at that instant is 20 meters per second. It's being squared over 100 meters. And this is going to be 400 over 4. This is going to be 4 meters per second squared. So that's going to give us the value of the centripetal acceleration vector, 4 meters per second squared. The net acceleration is the vector sum of the two. Right? Now, in order to get to deal with angles, we're actually going to need, let's see, I'm going to need this angle right here. Here's how I can get that. From the concept of arc length. Right? Here's a distance s, here's a radius r, here's an interior angle theta. And what relates all those things is the radian through this relationship. Theta in radians is equal to arc length over radius. So in this example, the arc length, the s, that distance is 100 meters. The radius is 100 meters. This is just coincidence. So we're at theta equals 1 radian. I'll just clean that up a little bit. And I like, we've got the angle in radians. I'm going to go ahead and convert that to degrees. So you got 1 radian times 180 over pi. We'll convert that to degrees. So that's at about 57.33 degrees. Right? So this is now a known angle. That angle right there is 57.3 degrees. If I come over here and I draw a horizontal line, that's going to make this angle 57.3 degrees. This angle is going to be 90 minus 57, which is 32.7. Right? Now, the reason I got those angles is because ultimately I'm going to need an angle to get the acceleration direction. Right now what I'm going to do is I'm going to draw just a vector diagram for this picture. So, and I'll go ahead and just keep drawing these in red. Alright, I need some room here. I think we'll come down here. And I actually think I'll make myself here. So now the acceleration is the vector sum of these two things. Let's see, I'm going to draw the centripetal first. 4 meters per second squared. And then the tangential acceleration is something like this. 3 meters per second squared. Then the net acceleration is the vector sum of the two. That's going to look maybe something like this. And this is going to make a right angle. So the magnitude of that acceleration is no problem at all. By Pythagorean theorem, a squared equals 3 squared plus 4 squared. I'm just going to put a little NCU for note consistent units. And that acceleration, if you work, it ends up to be 5. So at that instant, the net acceleration is 5 meters per second squared. All right. I'm going to go ahead and find this angle right here. I'm going to give it a name, alpha. The tangent of the angle alpha is equal to 3/4. So we're going to need the inverse tangent of 3/4, which is 37 degrees. All right. So the net acceleration vector is has a magnitude of 5 meters per second squared, and it's 37 degrees clockwise from the centripetal acceleration vector. So in this picture, I think that's probably good enough to just basically call this done, but in the original picture that puts the net acceleration vector about like this, where this angle is the 37, and that's going to make this one 57.3 minus 37. I'm just going to say 57 minus 37. I think that's basically 20 degrees from the negative x-axis. So picture got a little messed up here. Let me run through the highlights of this problem though. So at t equals 0, car starts here. but the driver gives it gas and accelerates at 2 meters per second, which we're going to assume constant for this problem. We're trying to find the acceleration vector 10 seconds later. It's important to realize that the acceleration vector has both a tangential piece, which we already know, and a centripetal piece, which is equal to v squared over r, needs to be calculated. So in order to calculate the centripetal, we need to know a couple of things, one of which is how fast the car is moving. So that's what this piece is about. Tangential accelerations equal to change in v over change in t. Calculating the change in v, we get 20 meters per second. So 10 seconds later, the car is moving 20 meters per second. That allows us to calculate the centripetal acceleration by v squared over r. The v being the 20, the r being 100. Now we also need to know where the car is. That's why I used the area under the curve here. That ends up being 100 meters. That told me how far along this path this car had traveled, 100 meters. Did a quick estimate here. 1/4 of a circumference, 1/4 of 2 pi r was, I forget what, something like 150 or 160 or something like that. But that put that car roughly right about here. Next, at this instant, now we need this angle a little bit more exactly. That comes from the concept of a radian, which is this stuff. Theta in radians is the ratio arc length over radius, which allowed me to calculate that at 1 radian and convert it to 57.3 degrees. So that tells me in this problem that's 57 degrees, which means if I draw a horizontal line at this instant, that also 57. Oh, let's see. Next is to add the vectors, right? The tangential, which is 3, to the centripetal, which came out to be 4. But you have to add them tip to tail. That's what this picture is about. So I drew the centripetal first at 4 meters per second squared. Then the tangential, right? And these are tip to tail, 3 meters per second squared. Pythagorean theorem gave me the 5 meters per second squared for the magnitude of the net acceleration vector. Next, this angle. And remember, this is the angle between the acceleration vector and the centripetal acceleration vector. So it's the angle between the net acceleration and the centripetal. It's the inverse tangent of 3/4, which is 37 degrees. Which means in the original picture, the net acceleration vector is 37 degrees clockwise from the centripetal acceleration vector. That would put it roughly in the direction shown. However, I've got that drawn a little longer than I should have. Maybe probably should look maybe more like this. Okay? And that makes that a 20-degree angle between the negative x-axis and the net acceleration vector. So that's it. That's probably enough for this one. Hope you enjoyed it. Have a great day.